thank you. So I think this clicker works. Okay. Okay. So what's the topic? Once upon a day, I was faced a concrete task. I need to evaluate the security of MDT DTM specification in less than 2 months. That was a business task, a business situation. I don't want to comment why I have so little time. That was my fault too. And the topic of my talk today is how to do it and stay alive. At first, I want to ask the audience how many people here are familiar with MDT DTM specification. Raise hands, please. One? One. Okay. So in general, MDT DTMs is for managing field devices. For example, on every ICS infrastructure, you have thousands of low-level field devices. How do you manage them? Because most of these devices, despite of working on traditional industrial protocols, they have different application layer, different vendor-specific commands. And how do you handle them? The one solution is DDL or EDDL, and the other solution could be FDT DTM. According to the maintainer of FDT DTM specification, the MDT Group, the MDT concept defines the interface between device-specific software components provided by device supplier, device vendor, and the engineering tool of the control system manufacturer. The device-specific software component is called DTM, Device Type Manager. And if you look to the PR articles by MDT Group, they show you that FDT specification covers almost all levels of the ICS infrastructure, from field and actuator, sensor bus till the remote maintenance. In fact, that's not really true, but you could easily find much DTM components at the middle layer, at the plant asset management system. You may use them, but you never know that you are using FDT DTM. So they are at DCS system, at SCADA system, at human-machine interface stations, and probably at manufacturing execution system. And how it works? The simplified FDT DTM architecture is given on the slide. And okay, and we have a frame application here. It is a container that holds a bunch of DTM components. The components are divided into the two types: the device that talking to the application layer of the field devices and realizes their specific vendor protocol, and comm DTM that acts with the industrial bus and talks such protocols as HART, Profibus, Profinet, Modbus, and others. And according to FDT DTM specification, DTM has a multi-layer concept. So if you have a distant field device that is on the HART bus and you want to access it from the station that connects to the HART through the chain of different gateways, like from Ethernet to field bus, from field bus to HART, etc., you need to set up a chain of comm DTM components, and then in the application you just talk to the final component, the device component, and all other things is done automatically. The encapsulation process began, and then the packet will go up through the components and then down to the system. And this all looks great. If you read the FDT Group site, you will find many, many great things about DTM. But in fact, if you look deeper, if you dig deeper, you will find that this specification is like a cart house. The internals are a bit messy, I think. The common object model, Visual Basic, .NET, ActiveX, XML, custom XML parsers, different thread models, JSON, and other things. And if you look a bit deeper, you will find such pretty XML parsers as on the left on the screen. You will find that using the common object model allows the attacker, if he compromises at least one DTM component, it will allow him to compromise the whole DTM container with all other components and frame application. Also, the usage of XML as the internal exchange format between components is rather optimistic, I think. So if you look even deeper and look into the internals of the specification, it's like the pose of this cat. It's all, I don't know how to tell it in English. It's spaghetti architecture. It's over-engineered spaghetti architecture. I'll return to the research scope. We've decided to take a sample of all DTMs and found out how many of them have weaknesses, what are the weaknesses of the technology, and thousands of such DTMs could be found at the official project catalog at MDT Group site. We need to get some sample of this, and we decided to take 10% of specific protocol DTMs. In our case, we choose 10% of all HART device DTMs. Why HART? Because I've already done some HART researches, I have tools, I have skills, and that was easy. In fact, if I choose, for example, Profibus, I couldn't do it in 2 months. And we've chosen 10%. It was 114 device DTM from 24 vendors for 752 devices. And there is another easy question in the research, how to fuzz such amount of components in 1 month, and why it could be hard. Because of different thread models, various implementations in the various languages, different vendors understand the specification differently, and that also causes troubles. And of course, we want just to fuzz application layer, so we want to fuzz device DTM component, and we want to exclude the other components from the fuzzing. We want to exclude the frame application from the fuzzing. We want to exclude the comm DTM component from the fuzzing. But unfortunately, you cannot fuzz just device DTM. You should fuzz all it together, because device DTM won't work without proper comm DTM or frame application. So we need to something to do with this. The other problem is the various licenses of DTMs, because some companies allow to run the DTM components only in specific frame application. For example, Anderson Hauser allow to run some of the DTMs only in field care. And the HART protocol is also slow, and we need a fast fuzzing. And moreover, some really weird device DTM requires real loop with a real current value, and that's the problem. And as I've said, different custom HART commands are for every vendor. Every vendor have specific application layer, and unfortunately, device DTM will send the next command to the device only when it gets correct answer from the previous command. So to fuzz, you need a state-based fuzzing, and you need a generation-based fuzzing, and you need to know, and you don't know the exact commands. So I explain it a bit. Remember the HART packet. It has 5 blocks. The preamble, header, and checksum is handled by comm DTM, and the command and data is handled by the device DTM. The comm DTM is sent XML binary stream from it to device DTM. And the HART command could be divided into 2 categories. The lower commands that are described in the HART specification, but some of them, of course, may differ from vendor to vendor. And the upper layer commands, the application layer of the HART protocol. And here we don't know packet format, usually, and usually we don't have any documentation from vendors. I should mention only Honeywell and ABB. At least them have documentation. Other vendors don't have such documentations in public. So I wrap up the problem list, and then I started to solve this one by one. The key idea is to leave external fuzzing only to the special cases, to the special components, and fuzz just device DTM, target the device DTM. So we need somehow fuzz from inside, fuzz inside the container without building the infrastructure around it. For most of components, we succeed with this. And here, how we done it. We just got the architecture and replaced the frame application and comm DTM with our custom written components. So we have direct access to the device DTM. So we could fuzz from the site. This is the idea sketch. So we replace the frame application with a custom frame application that we called fuzz frame. We have target device DTM, and the frame application, when we want to fuzz component, just send a command to target device DTM, read the device parameters, download all information from device. Then the target device DTM thinks that he talks with real line, but he talks with our custom comm DTM, HART fuzz DTM. And this component talks to the protocol parser and stateful fuzzer. Here is the sketch of parser and fuzzer. We have 3 fuzzing modes. The white noise fuzzing for unknown commands. If we don't know the common template, the common structure, the application layer structure, we use white noise fuzzing. For other things, we use random mutation fuzzing. And the question is still how to keep state and do smart fuzzing when you don't know the packet structure. So we need somehow to know it. The solution is really silly and dumb. We just do it in 4 steps. But it works. It really works. It surprisingly works very good. So we receive a command request from device DTM. If we have no information and no template for this command, we do some white noise generation for random length and send back. If we receive the next command that we are lucky, then we are lucky, and we could take this our generated white noise as a somehow template. Then we will do some advanced fuzzing with this template. In other case, we just repeat, and it works. Surprisingly, it works great. The other question was to choose the fuzzer. I was completely lost when selecting correct fuzzer. I talked to Adam, and the edges is good, but I have very little time to dive into new framework. And well-known HART Commons covers only the 20% of the whole fuzzing scope. So pitch and zoof would be good, but overhead here. We need something that fit in the task. And I've decided to stick with the silver bullet of fuzzing, the Radamsa, but I've slightly changed the Radamsa. I fork it and change it to make it fit into my task. So I called the fork Erlamsa because I forked it to Erlang. And it implements almost all Radamsa mutations in the same way, excluding XML mutations, because I need advanced XML mutations here because of internal exchange between DTM components are done with XML. So I developed 2 new XML mutational fuzzers and modified some binary mutations, add some length field prediction, binary structure prediction, very, very, very simple predictions, but maybe reliable mutations, and modified some ASCII-based mutations to make they work more correctly in case of FDT DTM. I think that's not a magic or not a completely new tool, but it's just fitting the old good Radamsa into my task. So how the fuzzing structure is look. So we have eHART fuzz. It do the template managing. It do the generation-based fuzzing. It manages templates, and it creates new templates. And when we have a template, we could send it to Erlamsa. The eHART fuzz interacts with the comm DTM component over the TCP UDP. And it receives the HART command number and returns the XML binary stream and data that could be easily sent to the target device DTM. The other question was to exclude frame application from fuzzing. We done this by creating a simple command line based FDT frame application. It do simple tasks. It emulates the FDT frame operations. initialize the comm DTM and device DTM, then calls read from the device DTM function, and connects back to the fuzzer via UDP for controlling the current state of the component and also for detection of non-critical bugs, bugs that won't crash the whole container, such bugs like XML injection, SQL injection, and others. The screenshot of the fuzz frame is on the slide. If we have to fuzz the specific device DTM that need the licensed frame application, for example, I mentioned already the Anderson-Hauser application and Anderson-Hauser components, we do it using AutoEat. AutoEat is a GUI testing tool. It's a popular tool in quality assurance. What we need to do is just write simple scripts. The script language of AutoEat is based on WebScript, so it's easy. You can see the example AutoEat script for Anderson-Hauser on the screen. And now we, of course, in this case, we are fuzzing a frame application too, but we have no choice in this case because breaking the license is not very good, as I think. And to solve the speed problem and exclude the comm DTM from fuzzing, we write a custom comm DTM components, and it works based on the architecture that's shown on the slide. So the target device DTM send XML with command ID to the HART fuzzer, pretends it will do the real work, the real interaction with the hardware. But in fact, it sent the command to the eHART fuzz, gets the result, and send back the XML binary stream. If you look our component in the frame application, for example, in field care, you will see that there no difference from the typical comm DTM components. You can use it. It's a standard comm DTM components, but it's interact with fuzzer, not with real hardware. The other feature of HART fuzz DTM is logging. We log everything. So every command that's sent back to the target DTM, every command that flies within the container is logged. That helps in situation when the component is crashed, so we got a bug, and we need to reproduce the crash. So total logging helps out to find where it's crashed and why. But in some rare cases, for example, for ABB device DTMs, there is a strange threat model and strange behavior or requirement of real timing or accessing the real hardware. And there are two solutions. In case where we don't need to access the real hardware, we could emulate the real timing using the virtual COM port, virtual serial port simulator, or if you require the real hardware, we could use ICS Cursor tool for emulating the device through the real current loop. In both cases, we need some service to manage the network and channel layer of HART. And I've used the library that I've developed this summer. It's a HART parser, Ruby gem, that used for working with HART on the network and channel layer, managing HART packet preamble, header, and checksum. For more information on the topic of ICS Cursor, I refer you to my talk on Blackhat USA 14, how I will pound your ERP through 420 milliamperes current loop. There is a cool demo there where I pound the SAP through current loop. So if you're interested in this topic, you could see this presentation. But sometimes ICS Cursor is not enough because in worst case, device DTM needs real current value of the loop. So I remind you how HART works. It creates the command from master to slave and from slave to master over some current bias. So this current bias represents an analog value of primary variable. For example, you have a temperature transmitter. And if the temperature is about 30 degrees, the current bias in the loop should be 11 milliamperes. And some DTM components requires this current. And unfortunately, I have no time to modify ICS Cursor to make it support the generation of such bias. But I found a rather simple solution. I've got a board from analog devices, evaluation board for maintain the current loop, and interconnected it with my ICS cursor. It was simple. You could control the ID 5421 IC over the SPI channel, and the HART-in pin from the ICS cursor is going to the HART-in pin of the IC, and HART-out goes directly to the current loop. And in this case, you just need to create the real hard current loop with the real power device and hard gateway. So I've solved all this problem and could show you the final architecture. In the simplest and the fastest case that works for almost 90% of the hard DTM components, we have such infrastructure where we have FDT frame, a target device DTM that we want to fuzz, the eHART fuzz and Erlamsa that do generation and mutational based fuzzing, that creates a new templates, that manages to mutate these templates, that holds state of the component, and it talks to the hard comm DTM fuzzer over UDP. There are two cases. If the component didn't require specific license, you just use fuzz frame. In other cases, you need AutoEat plus some vendor-specific pass or IMS system. In case when we have problems and need some real timings but not need the real current bias, we could use the hard comm DTM from code writes and interconnect it to the hard parser that will manage the network layer of the hard packet fuzzing using the virtual serial port by virtual serial port simulation application. And in the worst case, we need to create the real current loop and use the analog device evaluation board and ICS cursor to set up the real current over this loop. So finally, we've built an infrastructure, and the rest of the talk, I think I have 5 or 10 minutes, will be about the results. So when we started the fuzzing, just immediately we have the gates to the DTM kingdom opened, and we found many strange bugs from remote code executions to the XML injections. But I could not talk about it because responsible disclosure, the advisories, almost all advisories have been sent. I need to send about 5 or 6 advisories. We'll send them in this month. And just only bug got fixed until now from Emerson, but I think they fixed bug but they didn't understand the nature of the bug. Here is some nice diagrams. So we have about 29 vulnerabilities. We have a bunch of errors, but not vulnerabilities. Here only found vulnerabilities that could pose some risk to the industrial control system. I don't include found bugs. There are many bugs also. And these vulnerabilities triggers the 500 devices. So components that have vulnerabilities works with 500 different hard transmitter devices. And here are the types of vulnerabilities that we have found. It's race conditions, XML injections, denial of service, where just one denial of service will crash the whole DTM container along with other DTM components. Also, we have remote code executions with proof of concept exploits and possible remote code executions when we could do the memory manipulations, but we didn't wrote the proof of concept in case of it could be hard or we have no time. And the other vulnerabilities includes cross-site scripting, SQL injections, JSON injections, local denial of services when you crash just DTM but not the whole container, and other things. And here is the distribution by vendors of found vulnerabilities. I could give you a half of a minute so you could look at it. Rather cool diagram, as I think. And as I've said, only Emerson fixed the vulnerability. However, they don't understand the nature of vulnerability because in the advisory there is a paragraph that tells you need to have an access to current loop to trigger the vulnerability. It's a lie, it's an error, because due to multi-layer FDT DTM specification, you could just need to alter the packet from the device on every level of the ICS. So for example, if you have architecture like hard current loop, then hard to Ethernet gateway, and then the DTM component, you can meet the Ethernet packet and trigger the same vulnerability as you, for example, meet the hard current loop. So I think that's bad. They didn't understand the nature of FDT DTM while they developed the components for the FDT DTM. And some examples. This is not a vulnerability. This is a bug. This is a bug because you cannot. The payload for this cross-site scripting is very small. You just call alert or prompt or something, but you could not write some really evil code. But we have another cross-site scripting that could do some harmful to the system. I just show this screenshot because for me it's funny that triggering the cross-site scripting error from the analog current loop layer, it's really funny. And the other strange thing that I've met while reverse engineer some components is that very secure usage of memcpy. So as you can see, the second and the fourth arguments of memcpy S are the same. And these components are both from the user. So in this case, the memcpy S works like usual memcpy, so there is no security. They use security mechanisms without understanding the core of this security mechanism. And that's why they fail, and here we got a remote code execution because they don't understand how use memcpy S. And some results. I'm finishing. We have found 29 vulnerabilities from 14 vendors for 501 field devices. I have some good news. Recently, the FDT Group finally introduced a new version of FDT specification. The key differences of 2.1 specification from previous specification are .NET-based interfaces, and that fact that iteration between FDT objects is based on the .NET data types rather than XML. This is really good. But I have a bad news also. When I searched over the internet and asked the different vendors, I understand that there are no FDT 2.0 components. Specification exists, but no component exists. Moreover, the FDT2 has a backward compatibility to the previous version of FDT. So in case of mixed architectures, you have the same XML transport and the same vulnerabilities will exist. And moreover, if they will write the components in that way that have to do until today, they will call the managed C++ code from the unmanaged .NET code. Unmanaged C++ code from managed .NET code, and that's not good. That's the same as using just simple C++ without .NET. Here are the links to the developed tools. Unfortunately, I could not publish the fast frame, HART DTM fuzzer, and eHART fuzz before at least 90% of the bugs will be fixed. I hope that when the next S4 event comes, this will be published. Really hope. But of course, you could get the HART parser from the HART parser repository. You could get ICS Corsair, and I will publish the Erlams, I think in February or March. And Thanksgiving service, usual. Thanks to company that I work for, Digital Security, thanks to my colleagues Gleb Cherbov, Svetlana Cherkasova, Andrei Bakumov, and George Nosenko for participation in the research. Thanks Aki Helen for magnificent Radamsa tool, and Adam Crane for really useful advices. So I finished. Sorry for my really bad English language, and if you have a questions.
That's really good. So let's, if you have any questions, can you can either send them in via email to ask4question@digitalbond.com or raise your hand and ask a question. I did have a little question on your team. So you put their names up there, but did you track how many hours or how much time you spent doing this work on the project?
I think it was really fast. I think after we created the fuzzing infrastructure, it takes us about 20, 30 hours to fuzz and found all these bugs, and then about 20 hours to understand the bug's nature. But the creating of fuzzing infrastructure takes about a month because it was a hard task.
A man month or the team working?
For all the team, but in fact I work the whole time on this project, and other people just help in some things.
Other questions? Oh,
Jason.
one up here. Please introduce yourself.
Hello, Jason.
Oh, Jason Larson, IOActive. So you got to fuzz a whole bunch of different devices. Is there a place where we could actually get a hold of all these devices and try various fuzzing techniques? One of the things we never really get to see on fuzzers is fuzzing techniques versus fuzzing techniques to get them kind of a apples to apples bake off. Since you had so many devices, I was wondering if there was a repository someplace that we could actually go play with.
In fact, if I have these devices in real, so if I bought all these field devices, I don't need to solve such hard task because I just need to sniff the traffic and do mutational and generation based fuzzing. But as you can see, the amount of device that we have found, that we have fuzzed, we have only software components from them. And to reverse engineer the whole application layer, it was a really long task. We don't have so amount of time. And what we just do is try to emulate the real device and try to predict what field device could answer to the device DTM request. So in case to solve this task, I need to reinvent the bicycle and write such strange infrastructure. Of course, if I have all these devices from the vendors, it will be simple, just generation-based fuzzing, as I think, based on the snippet traffic. But I think if we got all the such devices to our office, we have no place to work.
Okay, great, thanks. I did get a question here on email. I'll try to summarize it, but they said that you took a 10% sample.
10% sample, yes.
Yeah. And do you think that if you were to extrapolate the results, is there any?
No comments on this. I don't know. I think maybe if we have some time, we could take a 25% sample and repeat the task to see how this could extrapolate. But I have no comments now. Maybe not.
Let me say it a different way. Do you know of any reason why the extrapolation would be wrong? So you don't know it's right, but you know of anything that makes you worried about the extrapolation of the results?
Don't know. It could be just random. I don't think that extrapolation here, that I could extrapolate. After we have a talk at Blackhat Europe where I don't discuss fuzzing, just present the results that I've presented in the last slides of the talk. Some news portals extrapolate, but in fact I have a talk with some journalist and tried to tell him that he could not extrapolate because it's strange and it could be wrong.
Okay. We'll take one more question. What do I do with my mic? Oh, Jason has it.
Hi, it's Mike. Since these are comm objects, all right, and
yes,
you can call up the comm object on your own and make it run on its own, is there any reason why you couldn't use that as maybe leverage within the system to execute privileges higher? That would be my question.
It's not just comm object. In fact, the first idea was, let me put it in the comm radar and do the task. And that won't work at all, because the FDT DTM specification is rather strange. There are much of different interfaces, so the same object could be called like one comm interface, like other comm interface. The interaction is based on the comm objects and XML. It's mixed, and we've tried to write some scripts from CommRadar, and we failed because we thought it will be very hard. It takes too much time. So to make the fuzzing faster and to fuzz the core component, we think that we just need to reinvent the FDT DTM infrastructure. And moreover, some, as I've said earlier, some FDT DTM components require a specific license if they won't be run in the vendor-specific frame application. For example, Andreessen-Hauser, some Vega components, and some components from IFAC system, and other.
Okay, great. Well, thank you very much, Alexander.
Thank you.